When a model works well in a lab but struggles in the real world, the problem is often not intelligence, it is practicality. Real systems have limits on memory, compute, battery, latency, and cost, and those limits can quietly change how safe and reliable a security workflow feels. This is where model compression techniques like pruning and quantization enter the conversation, because they aim to make models smaller and faster without losing too much capability. For Security AI Plus, you should treat these techniques as engineering choices that have security consequences, not just performance consequences. If compression changes a model's accuracy, stability, or behavior under unusual inputs, it can change risk, especially in detection and decision support systems. Beginners sometimes assume that making a model smaller is automatically a win, but defenders know that every optimization creates a new set of trade-offs. The goal here is to understand what pruning and quantization are, how they work at a high level, and how to apply them in a way that preserves trustworthy behavior. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. To understand pruning, picture a model as a large network of learned connections that collectively shape its output, even if you cannot interpret any single connection easily. Pruning is the process of removing parts of that network that appear to contribute little, with the goal of making the model smaller and sometimes faster. At a high level, the idea is that many models are over-parameterized, meaning they contain more capacity than strictly needed for their task, and some weights or components end up being redundant. Pruning tries to cut away redundancy while keeping the meaningful structure intact. In security terms, this matters because redundancy can sometimes provide resilience, and removing it can make behavior more brittle, especially on rare or adversarial inputs. A beginner might think pruning is like deleting dead code, but it is more like trimming a complex ecosystem where a seemingly minor element might support stability in edge cases. When you apply pruning in a security-sensitive system, you are not only optimizing size, you are adjusting the shape of failure modes. There are different ways pruning can be done, but you can keep the mental model simple by separating unstructured and structured pruning. Unstructured pruning removes individual weights or small connections, often creating sparsity, which means many connections become zero and can sometimes be skipped during computation. Structured pruning removes larger chunks, like entire neurons, channels, or attention heads, which tends to produce models that are easier to speed up on common hardware. The security angle is that structured pruning can change model behavior more visibly because you are removing whole functional subcomponents, not just trimming tiny contributions. Unstructured pruning can also be risky because the performance gains might not appear unless the serving environment can exploit sparsity correctly, and misalignment between design and deployment can create unexpected latency or reliability issues. For defenders, the important point is that pruning is not one thing. It is a family of choices that trade model capacity for efficiency. A good security mindset is to treat each pruning approach as a different change with different validation needs, not as a simple checkbox that says smaller equals better. A common reason pruning matters in security workflows is that many deployments have tight latency budgets, and latency can translate into risk. If a detection model takes too long to score events, alerts arrive late, and late detection is sometimes equivalent to no detection. If an interactive system takes too long to respond, users may retry, bypass, or revert to unsafe shortcuts, which creates operational risk. Pruning can help by reducing compute demands so the model responds faster and fits in constrained environments. The risk is that the speedup may come at the cost of degraded recall, meaning the model misses more threats, or degraded precision, meaning the model floods analysts with noise. The worst-case failure is a model that looks fine on typical traffic but becomes unreliable under the exact unusual patterns that indicate an attack. When you hear pruning in a scenario, you should automatically connect it to these trade-offs: improve performance and lower cost versus potential loss of edge case reliability and robustness. Quantization is a different kind of compression, and it often delivers improvements that are easier to realize in practice. Quantization reduces the numerical precision used to represent model weights and sometimes activations, moving from higher precision formats to lower precision formats. At a high level, this makes the model smaller in memory and faster on hardware that can compute efficiently with lower precision. The key concept is that the model's math becomes approximate, and the hope is that the approximation is close enough that behavior stays essentially the same. In security contexts, approximation can be safe if it preserves decision boundaries, but it can be dangerous if it increases uncertainty, instability, or sensitivity to small input changes. Beginners sometimes assume that quantization only affects speed, but it can also affect accuracy and calibration, which are central to risk decisions. If a model's confidence scores become less reliable after quantization, you may make worse threshold decisions and change the balance between false positives and false negatives. Quantization is a practical tool, but it is still a behavioral change that must be validated. One of the easiest ways to think about quantization risk is to imagine that you are rounding numbers inside the model. Rounding can be harmless when values are large and patterns are strong, but rounding can be harmful when the model relies on subtle differences. In security detection, subtle differences can be exactly what separates benign from malicious in rare cases. Quantization can also introduce uneven error, meaning some types of inputs are affected more than others, which can create fairness and coverage issues across systems, users, or traffic types. Another security concern is that quantization can change how a model behaves under adversarial perturbations, where an attacker makes small changes to inputs to flip a classification. If quantization makes the model more sensitive or less stable, it can become easier to evade or manipulate. The practical beginner misunderstanding is believing that a model that passes a quick accuracy check after quantization is safe to deploy. A defender would demand deeper checks that include edge cases, threat-like inputs, and stability over time. Pruning and quantization also intersect with the concept of trust in model outputs, especially when those outputs drive decisions. In many security workflows, model outputs are not final truth. They are signals used to prioritize investigation or to trigger automated controls. If compression changes score distributions, even without changing overall accuracy much, it can alter operational behavior. A model that produces slightly lower confidence might cause fewer events to cross the alert threshold, increasing false negatives. A model that produces slightly higher confidence might cause more events to cross the threshold, increasing false positives. This is why accuracy alone is not enough. You also care about calibration, separation, and how thresholds behave in production. A defender's validation mindset is to examine whether compression changed decision patterns, not just whether it changed overall correctness on a test set. In exam scenarios, the safest answer often involves revalidating thresholds and monitoring alert volume and miss rates after compression rather than assuming the old operating point still applies. Security expectations are not only about accuracy, they are also about predictability, auditability, and safe failure. Predictability means that when inputs change gradually, outputs should not jump unpredictably, because unpredictable jumps are hard to govern. Auditability means you can justify why a system was chosen and how it was validated, even if the model is complex. Safe failure means that when the model is uncertain or degraded, the system should fail in a way that limits harm, such as escalating to human review rather than taking irreversible actions. Compression can stress these expectations by introducing small numerical changes that become large behavioral differences in certain regions of input space. A beginner might focus only on the average case, but defenders worry about the worst credible case because adversaries aim for worst cases. This is especially important for systems that operate at scale, where even a small percentage change can translate into many missed detections or many false alarms. When a scenario mentions applying compression in a production security system, you should be looking for controls that preserve predictable behavior and safe fallback modes. A strong defender approach is to treat pruning and quantization as controlled releases that require evidence before and after. Before compression, you establish a baseline, not just with accuracy, but with precision, recall, and any operational measures that matter, like alert volume per day and average time to triage. You also identify the critical slices, such as rare attack types, high-value assets, or high-risk user groups, because those slices are where degradation is most painful. After compression, you compare performance on the same baselines and slices, looking for regressions and behavior shifts. You also validate under realistic load, because a model that is faster on paper might behave differently when deployed at scale due to hardware constraints or concurrency. The key is that validation must be aligned with risk, not aligned with convenience. In exam terms, this mindset often points you toward answers that emphasize pre-deployment benchmarking, post-deployment monitoring, and rollback readiness rather than a one-time accuracy check. There is also a supply chain-style security angle to compression, because compressed models can change how artifacts are handled, stored, and distributed. A smaller model is easier to copy, which can be good for deployment, but can increase the risk of unauthorized distribution or model theft. A compressed model might be deployed to more endpoints or more environments, increasing the number of places it must be protected and monitored. Compression pipelines themselves can be targeted, because if an attacker can influence pruning criteria or quantization settings, they might be able to intentionally degrade performance or create a subtle backdoor-like behavior shift. Beginners sometimes think of compression as a harmless optimization step that happens after training, but defenders treat every transformation step as part of the model lifecycle that needs access control and integrity checks. The goal is not paranoia, it is consistency, because attackers target weak links, and transformation pipelines can be weak links if governance is lax. A well-run process tracks versions, validates checksums, and limits who can modify compression parameters. Another important connection is how compression interacts with drift and ongoing operations. Even if pruning or quantization is safe at deployment, drift can change the input distribution over time, and compressed models might have less capacity to absorb that change gracefully. If a model is already closer to the edge of acceptable performance due to compression, a small drift can push it over the cliff. That means drift monitoring becomes even more important after compression, because the safety margin may be thinner. It also means you should plan for periodic revalidation and potential recompression if the model is retrained or fine-tuned later. A beginner might imagine compression as a one-time step that locks in efficiency forever, but real systems evolve, and each new model version may require new compression decisions. In exam scenarios, when you see a compressed model degrading over time, the correct defender response usually involves checking for drift, revalidating on recent data, and considering whether the compression trade-off is still appropriate under new conditions. Beginners also tend to assume that pruning and quantization are purely technical choices, but they often reflect business and governance constraints. If a system must run on limited hardware, the organization may accept some accuracy loss to achieve feasible deployment, but that acceptance should be explicit, documented, and monitored. If a system is used for high-impact decisions, like automated blocking, the organization may require stricter performance thresholds and may limit compression to preserve safety. These choices should be tied to risk appetite, which is a governance concept, not a model concept. In practice, this means defenders should be involved in compression decisions because the impact is not only latency and cost, it is missed detections, noise, and the possibility of adversarial exploitation. The exam often tests for this kind of cross-cutting thinking, where the right answer recognizes that technical changes must be justified by risk and backed by validation gates. Compression is not an excuse to lower standards. It is a reason to clarify standards. A common misconception is that if the model is smaller, it must be more secure because it has less complexity. That sounds appealing, but security does not automatically improve when complexity drops, because you can reduce complexity and still create new weaknesses. For example, a pruned model might be easier to evade if its decision boundary becomes smoother or less nuanced, and a quantized model might become more sensitive to small input differences. Another misconception is that compression always affects all classes equally, but in many real cases the degradation is uneven, hitting rare patterns harder. A third misconception is that a model that remains accurate on a curated test set is safe, when the test set may not include adversarial behavior, unusual log artifacts, or the kind of drift that happens in production. Defenders correct these misconceptions by testing where it hurts, not where it's comfortable. When you apply pruning and quantization in security systems, you must assume that attackers will explore the new behavior surface and that operational noise will stress the model in ways the lab did not. To keep your thinking practical, it helps to connect pruning and quantization to a simple decision framework that matches defender habits. First, name the goal, such as lower latency, lower memory, or lower serving cost, and be honest about why that goal matters for the system's security outcomes. Next, identify what cannot be compromised, such as minimum recall for critical threats, maximum acceptable false positives, or stable behavior under known edge cases. Then, treat compression as a controlled change. Compress, validate on holdouts and critical slices, test under realistic load, and monitor after deployment with clear rollback criteria. This framework is not about slowing progress. It is about preventing efficiency work from becoming an unforced security error. If a scenario question asks what to do before deploying a compressed model, the best answers will often include this sequence of baseline, controlled change, validation, and monitoring. Defenders are not anti-optimization. They are pro-evidence, and evidence is what keeps performance work aligned with risk. The main point to carry forward is that pruning and quantization are ways of trading model capacity and numerical precision for speed and size, and those trades must be evaluated like any other security-relevant change. Pruning removes parts of the learned structure, which can reduce redundancy and sometimes reduce resilience, especially on edge cases. Quantization introduces approximation, which can change score behavior and stability, even when headline accuracy seems fine. Applying these techniques safely means validating not only overall correctness, but also the operational outcomes that matter, such as alert volume, misdetections, and the reliability of thresholds. It also means treating compression as part of the lifecycle, with version control, integrity, access control, and drift-aware monitoring. If you can explain these ideas clearly, you'll be ready for security AI plus questions that ask you to choose the safest deployment decision under resource constraints. Optimization becomes safe when it is paired with disciplined validation, and disciplined validation is the defender's way of turning clever engineering into trustworthy security outcomes.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.